Hello and welcome to Speech and Hearing Science. This is the first class and we'll speak about the nature of sound, and that is the first chapter of your textbook. Please listen to this lecture and come prepared to answer questions about it. I will be posting a quiz online and you will have more details in the syllabus. It's very, very important to come to class after having listened to this presentation, and we are in the class, we are not going to go over material page by page, slide by slide. So this is your presentation, and in the class we are going to do a lot of activities and I'll answer any questions that you will have. So let's start. First, we are going to go over some basic concepts. So these basic concepts, you need to first understand them, and then you basically need to be able to identify them. In other words, you need to basically memorize them. They are basic concepts. So acoustics as a field is the field of physics that deals with the production, control, transmission, reception, and effects of sound. We are going to go over each one of these to explain in detail what each one means. Production is making the sound. It could be, we are speaking about acoustics, it could be any sound at all, human, non-human. So we speak about what makes what makes the sound, how that sound is made, whether that's a cricket, if it's a bird, a human being, a car, you name it. Control of the sound in terms of, is it loud, is it low sound, soft versus loud, is it high pitch, low pitch, transmission of the sound, how the sound travels through air from one person or one animal to another. So this production and reception are two spots. Like say I produce a message, you receive the message. In between you have transmission. So reception means getting the sound and making sense of it. So hearing it first, and then it reaches the brain, and then we figure out what that sound means, what the message that is encoded in that sound means. For example, animals make different sounds, and each sound has a meaning. So again, the four components that we've spoken about: production, control, and transmission, and then reception. And the effects of that sound on the receiver, obviously. Someone says something, you might get startled, or someone might say something, and you are going to say something in return. So again, the person who produces the sound controls the sound, and then the sound travels through air or water or whatever it is, and then on the other side you have a receiver, someone or an animal that gets the sound, and then the effect of that sound on the receiver of the sound. Bioacoustics now speaks about a particular, it limits the concept to living things. Bio means living. So biology is the science of the living or living creatures. So bioacoustics is the science that deals with the production and perception of animal sounds, including humans. So any living creature that makes a sound, then if we study that sound, how it is made, how it is produced, how it is controlled, transmitted, how it is received, and what effects it makes, then in animals, by animals, then that will be bioacoustics. Because sound deals with pressure, and sound is the result of force. We need to study different general terms, and that will help us calculate sounds and understand how sounds are generated. So first we have the system that is used in the US. We use miles, we use inches in terms of distance. We also, for weight, we use pounds, ounces, and in terms of liquids, we use gallons, pints, and so on. These systems are large because the US is a continent. If you say, okay, let's measure in kilometer, everything is going to be all like, 50% more than it is. So the metric system uses smaller units, and the smaller you are when you measure things, the more accurate, obviously, the results are going to be, they will be accurate in American systems, but it is like this. If I have an exam that has 1,000 points, like the whole course, say 1,000 points, and then you have an exam that's 100 points, or an entire course that's 100 points. Obviously, if someone loses 1 point, you are speaking about in the 1,000 scale. So the metric system, or the international system of units, it makes you see smaller things on a scale. For example, when you see temperatures, actually not temperatures, the distances. A mile is 1.67 or something like that of a kilometer. So the kilometer is smaller, and 1 kilometer is made out of 1,000 meters, and what each meter has 100 centimeters. If you compare this to the mile, and then the yard, and then the inch, the yard is a little bit smaller than 1 meter, just about 4 centimeters smaller. But in the end, the mile is 1.6 more than 1.5 miles, 1.67 of a kilometer. So the system that we use in science, that is the international system of units, the meters, kilometers, and then seconds. And then on a smaller scale, we are going to use centimeters, and then for distance. Centimeters, as I mentioned, 100 centimeters equal 1 meter, and 1,000 meters equal 1 kilometer. Then grams are weight, and 1 gram, or if you would like to see how much 1 gram is, a penny is equal to 2.5 grams, 1 penny. So the bigger unit for a gram is kilogram. A kilogram has 1,000 grams. To give you an approximate estimation, 1 kilogram equals 2 pounds and 1/5 of a pound, 2.2. So if you have can think about anything that's 1 pound, put two together, and then put 1/5 of a pound, then that will make 1 kilogram. So again, just keep in mind that the MK, miles, kilometers, and seconds, that is for large distances, and large distances, like say a bridge. You want to measure how big the bridge is, a distance from let's say a town to another town, kilometers in kilometers. But the CGS, or centimeter gram per second, the centimeter obviously is a small unit of measurement. 1 inch equals 2.5 centimeters. So the centimeter is used because what we are dealing with, little systems, small systems, like how big is the eardrum, and how much weight will the pressure from your sound, how much force will it put on my eardrum to vibrate it. So this is the centimeters, grams, and seconds. These are what we are going to use for the most part, because we are dealing with very, very small structures. So that would make sense. Mass is defined as the amount of matter in something, in an object or anything. For example, you can look at this marker and say, how much mass is there? If you are scientifically, like you want to get it really, really scientifically accurately, you measure how many molecules are in there. Then and then you weigh these molecules and say, you can estimate the mass. So mass is not about how big something is, it's about how much material is, there is. It is measured in kilograms. It's measured also in grams, depending on how big the thing is. So for example, if you say, I have a key, what is the mass of this key? You basically speak about the weight. Obviously, things that have a lot of mass in them, they weigh more. If you have, say, let's say a box like this, and you fill it, whatever there is in it. You focus more on the material that is in there, atoms in the box and inside, whatever it is. And then you say, what is the mass? So mostly mass is estimated based on the weight. And again, it doesn't have anything to do with size, big or small. It is the weight. Density has to do with how closely the molecules or the atoms how closely are they packed in one, something, how densely are crowded into something. For example, if you have this box and you fill it with sand, and then you have another box just like it, exactly the same box, and you fill it with cotton, and you don't push the cotton in, you just fill it just with cotton. Which one is going to be more dense, the one on the left or the one on the right? If you said sand, obviously you're right, because sand, the molecules are closer, the sand crystals are closer to each other, and then cotton, they are farther apart, or sponge. So sand will be more dense than cotton, simply because there's a lot of air space inside of cotton molecules and around them. But in sand, you don't have much space there between one crystal of sand than another. And that means that there are more molecules of sand. If you count the atoms, you are going to find many more atoms here and in the sand box, and when the box is filled with sand, and much less atoms in the box filled with cotton. So density, it usually affects size. Things that are less dense, they are usually they could look bigger in some cases. Things that are dense, they are really condensed. Like, for example, if you have let's say one container, and you take 1 cubic inch or 1 cubic centimeter out of the sandbox, and that is the amount of sand that's in 1 cubic centimeter or 1 cubic inch. That is going to weigh much more than a cubic inch that is filled with cotton. So even though they look the same size, when you weigh them, the one that has more density in it, things are more condensed, that is going to weigh more. So things that are high density have greater mass, and things that have less density, they could look larger and so on, but they are going to have less mass. So a pound of sand and a pound of cotton. The pound of sand, even though they were the same, is going to be much smaller than the pound of cotton, even though they both have the same mass, 1 pound, 1 pound. But again, which one is more dense? The pound of sand. Force is defined as any influence that causes an object to undergo a change in 3 things. A change in speed, a change in the direction of movement, or a change in shape. So I have a little globe. Obviously it's made out of sponge, and I'm going to put some force on it. Now, how did does this definition apply to what I am doing? I am putting some force, and I'm changing the shape of this ball, the shape. So that's one example. Or I could take this ball and kick it. How much I'm going to kick it is going to determine how far it will travel. So that is force. Again, moving something or changing its direction. Like this is coming at me and I'm going to hit back, I'm going to change its direction. So anything that does that, we say it has, force. It has force that deals with it. So how do we measure force? We measure it by, in newtons or in dynes. The difference between the two is that newtons are larger units. Dynes are very small units. For example, we use dynes to measure the pressure of air, as you speak, on the eardrum, because the eardrum is 0.55 of a centimeter. So that's approximately 1/3 of an inch square. So 1 Newton is a force that accelerates a 1 kilogram of mass at a rate of 1 meter or 1 second squared, depending what you deal with. So again, it's a force, how much force you put into moving 1 kilogram of mass at a rate of 1 meter per second. Like I say, let's say I have this box and this 1 kilogram, and I'm going to throw it to someone. And you measure my distance from where I am, and you say 1 meter away, about 3 feet, roughly 3 feet away. If you are standing 3 feet away and I throw this box, then the amount of force that I put that can make this box reach you when I throw it, that will be 1 Newton. So you see how it is? This is 1 kilogram is a big, weight. And we say per second. So if when I throw it, to you, obviously it could take about 1 second from the time I let go to the time that you catch it. And the distance will be about 3 feet in between. Oh, if we are standing 3 yards away, how many newtons will that be? If I have the same 1 kilogram of mass and I throw it to you, and you are 3 feet away, 3 yards away, or let's use scientific measurements, 3 meters away. How many newtons will I need in order to throw or to make this kilogram reach you, and how many seconds will I use? If it takes 1 second, it takes you 1 second to throw 1 kilogram of mass 3 feet away so it can reach you. How many seconds will it take to make a kilogram of mass reach you when you are 3 meters away? Obviously, it will take 3 seconds. And again, you have 1 kilogram. When it travels 3 meters away, that is going to equal 3 newtons of force. So now, let's look at the dyne. A dyne is a force that accelerates 1 gram of mass at a rate of 1 centimeter per second squared. So if I have, let's say, a piece of metal. I can't think of something that is just 1 gram. Let's say a little piece of metal, and I'm going to throw it to you. Or I could simply just flick it with my finger, and I put markers there, say 1 centimeter, 2 centimeters, 3 centimeters, 4, 5, and I take that penny and just, flick it to make it move 1 centimeter, and at a rate of, make it move 1 centimeter, then I have moved it. I could say the amount of force that my finger put was 2.5 dynes. Why? Because the penny is 2.5 grams. So if I have, let's say, maybe 2 pennies together, glue them together, and then flick them with your finger, and you make them move away 1 centimeter. So how many dynes will that be? It will be 2.5 grams plus 2.5 grams. That gives you 5 grams, which is the 2 pennies. And if you flick them 1 centimeter, then you have put the energy that you have put into flicking them away by 1 centimeter is, can you calculate it? How much force? That will be 5 dynes. Because again, there are 2.5 grams in 1 penny, and then 2 pennies you have 5 grams. When you accelerate them by 1 centimeter, that means each gram required a force of 1 dyne to move to 1 centimeter away. If you find, let's say, a smaller, object that's very small, just 1 gram, and you flick it, make it move or speed by 1 centimeter per second squared, then that you will have expended 1 dyne of force. So, in summary, 1 Newton equals 100,000 dynes. So a dyne is a very, very, very tiny unit of force. Then we move to other concepts, including volume. Volume, when you think of it, you think about sound, like is high volume, low volume. But volume means more than that. A volume is the quantity or the space, the quantity in a three-dimensional space that is occupied by a liquid, a solid, or a gas. For example, the space in this lens cleaner, inside, is filled, with the liquid. And all the liquid that fills that container from the bottom to the top, from left and right, front to back, all of that is the volume that is ready to hold something. So the word has more than one meaning again. If I take this cover off and I pour all the liquid out of it, the space inside, that is the volume that can hold any liquid or solid or gas inside of it. And so I say, for example, if I have a bottle of water, say how much, and that is empty, how much can it take? Then say it's a half a liter. And in addition to that, the space that is enough to hold a half a liter, we also say the water that is inside, that water is also a half a liter. So it could refer to the space, and it could also refer to the quantity that fills that space, whether that quantity is liquid, solid, or gas. I am trying to simplify the concepts as much as I can. I mean, I know they are clear, and but I'd like to simplify them as much as I can so you can go back to them and understand them better. Speed is the distance that is covered by an object in a given unit of time. So in speed, you have two things that are essential when you define speed. Speed, you speak about how much distance you cover and in how long. So how much distance covered in a given unit of time. Like, for example, speed. What was your speed when you drove to class the last time? You say, well, I traveled 25 miles. So, and then you say, what? So, I mean, what does that mean? It will not be complete until you say per hour. So, until you say the time. So again, whenever you speak about speed, you have to give me the distance that is traveled by an object in a given unit of time. Velocity is similar. However, in velocity, there's a direction. The distance traveled by an object in a given unit of time, just like speed, in a specific direction. So, for example, a rocket, as it is launched, it goes up, for example, and it covers a certain number of miles in a given, unit of time, per second or per hour, and in a given direction, going up for example, or going horizontally. A bullet has, the velocity of a bullet. It goes from one point, the barrel of a gun, directly to another point in a pointed direction. So then we speak about Newton's first law, which is the law of inertia. Inertia means, or this law means, a body in motion or at rest is going to stay in the same condition, motion or rest, unless it is acted upon by an external force that changes its condition of motion or changes its condition of rest. For example, if I have this ball, put it somewhere, say on a shelf, it is going to stay there forever unless something comes to change its position or moves it away or acts upon it. Like, for example, air, or if someone knocks it off. If nothing happens to change its position or location or direction, then it will stay the same. Now, if this ball is, let's say I throw it away, according to the law of inertia, it should continue traveling. Or if I throw it up, it should continue flying up until or unless some force acts to bring it down. And of course, we know what that force is. It's gravity and also the pressure of the air pushing down on it. So this law is going to help us understand how air molecules travel in air, because when we make sound, we basically use air molecules. We send them away, and they bounce back at us. But before they bounce back at us, they hit other molecules, and these molecules travel and hit other molecules and then go back. And I'll demonstrate how this works. Elasticity is an extremely important concept. Elasticity is something that we can never live without. Your body, when it starts to lose elasticity, that means you are old, you are getting old. Elasticity is the force that causes a deformed structure to return to its original size or original shape or original form and its original location. So let's say, again, I have the globe here, and I'm going to put some force on it to deform it. So now it is not a globe anymore. And I'm forcing it down and distorting it. What do you think is going to happen when I take my fingers away? Okay, yes, you guessed it right. It is going to bounce back to its original shape. What made it bounce back to its original shape is elasticity. The ball has an elastic force. It is like when you have one second, let me get something. So when I have a balloon, now the balloon is at rest. It means nothing is forcing it out of its way. When I pull the balloon down, again, as I pull away, the tissue of the balloon has elasticity or has an elastic force. As I pull away, that elastic force pulls me back so that I can let the balloon go back to rest. The longer I pull, the greater the elastic force is gonna be that wants to bring back the balloon to its original position. So elasticity is found in tissue all over your skin Your skin has elasticity, and when it is pulled away or distorted, that elasticity will make the skin regain its shape and its form. If you go outside and squint to make these frown lines, because of the sun, your skin bounces back immediately. However, with aging, elasticity is gonna make it hard for the skin to go back. So you have some people just have these frown lines or the lines that are here or there because the skin loses its elastic force as time goes by with aging. Likewise, now I am forcing the tissue of the balloon to be expanded, to be distorted, to be away from its rest. What do you predict when I let go of the air inside of the balloon? Again, you guessed it correctly, because when I let go, the balloon, the elastic force inside of the tissue of the balloon is going to bring the tissue back to its original position, and in doing so, it is going to raise the pressure inside, and it will force the air out of the balloon. So, elasticity is critical in many ways. Number one, it enables us to understand how the vocal folds work. Vocal folds have elasticity. It enables us to understand how lung tissue works, how the diaphragm that helps us breathe in and out, how that works. And it enables us to understand how air molecules travel in air and how they behave as they hit other molecules, they bounce back. So when I take this, say, air molecule, and I speak, so I make it travel away and hit another molecule. Elasticity will make it go back to where it was. This is how air molecules behave. Additional concepts include energy, and energy means the ability to do work. It doesn't mean that you are using it. For example, when you say fuel, wind energy, or solar energy, or fossil fuels, all of these are forms of energy. Potential energy is the energy that you have or an object has, but it is not being used at the moment. For example, if I say, think about how many gallons of gasoline are in your car. So let's say five gallons. Your car is in the garage or parked outside. It is not moving. The gasoline inside of the car, as we speak, and the car is not moving, is termed as potential energy. Potential means it is going to give you the energy that you want when you start using it, but you are not using it at the moment. It is like stored energy that is ready to be used. Kinetic energy. Kinetic has to do with kinesis, or comes from kinesis, means movement. Kinetic energy is the energy, the actual energy that is used in order to move things, to produce motion. So, as you turn the key on and the car starts, now that potential energy is converted to kinetic energy. It is moving gears and it's moving things in the car and fans and all kinds of things. So it is now kinetic energy. So you want to say, well, how much am I burning? How much of that energy am I burning per hour, for example, or per, second? Then you say, oh, you are speaking about power. So power is the amount of energy consumed per second or per hour. It depends on what you are looking at. So you could say, well, if I let the car running for a half an hour, I will be burning, say, a gallon, or let's say maybe 1 gallon. So the power that is being generated by the gasoline that is burning, that is going to be the power. And an easier way to explain it also is you have a light bulb, and when you put the switch on, that light bulb is consuming energy. So you say, like, how fast? Well, if you leave it running for 1 hour, it will consume, or it will give you, let's say 40 watts in 1 hour. 40 watts of energy is going to be consumed by the light bulb in a single hour. There are light bulbs that are going to consume 10 or 12 or 13 watts per hour. And obviously, the less they consume, the better, because that will help us save energy. So again, energy is any form of energy that can make things work or move, and potential means it is ready to be used. It is stored, ready to be used. Kinetic is what is actually used now as we speak. And then power is how much of that energy, kinetic energy, is being used per hour or per second or per any unit of time. Intensity is the power per unit of area. Let's say, for example, you have a room that is 10 feet by 10 feet, 10 feet left to right, 10 feet front to back, 10 feet ceiling to floor. So how many, you measure that and say, in cubic feet. And then you have a light bulb in that room. The light that this, light bulb is going to generate, it is going to be distributed among all the units, all the cubic feet in the room. So you take every single cubic foot, and say, oh, this cubic foot of the room is consuming or needs this amount of lighting, and then that will be intensity. If you need more, obviously, if you have a bulb that has 120 watts per hour, it's gonna produce more lighting in that room. If you bring, say, a light bulb that's like, say, a night light, and put it in that room, it is not going to have much of an intensity. The light is not going to be as intense. So you think about intensity as when you divide things into smaller structures, and you say, how much will each inch use, or how much power will each inch or each meter or each cubic foot is going to use. We also use that in heat, like when you want to install, heat or air conditioning. You say, well, the room is 5,000 cubic feet, and each foot is gonna need this amount of heat, and then based on that you calculate the baseboards accordingly, or air conditioning as well. Pressure is the force that acts at a 90-degree angle on a surface of an object. So perpendicular means at a 90-degree angle. So 90 degree is the maximum amount of force that you can put on something. If you stand on a chair, the area under your feet is going to be the area that carries most of your weight. The pressure that you put is focused 90 degrees right beneath your feet. If you say you are standing on a table, as you stand in the center, then you if you measure a foot to the right, you have more pressure. Less pressure than the center under your feet. If you move away 2 feet, that area even has less pressure than 1 foot away. If you move 3 feet, so the farther you go away from 90 degrees, the less the pressure is going to be. How will that help us understand sound? Think about, this is an experiment I'd like you to conduct before coming to class. I'd like you to, as you speak with someone at home or anywhere, see what happens to the sound. When is the sound strongest? Is it when you face the person face to face? Will that sound be the strongest sound? Or when you turn away at an angle, let's say 20 degrees or 30 degrees, will that sound be stronger or weaker than looking at the person directly? Okay, turn to all the way to the side. Will that sound be stronger or weaker than the 30-degree angle? Turn all the way to the back, all the way around, and listen to the same person speak and tell me if the sound is weaker or stronger as you change your angle. So that is your experiment. I'm going to ask you in class about your observations about this. I'd like you to be able to explain what it has to do in terms of pressure. And as you read in the chapter in the textbook, you should be able to answer this question. So pressure is measured in pascals or in dynes. The difference is that pascals are bigger than dynes. Dynes are also equal to microbars. So pressure can also be measured in units, centimeters of water being moved up. The amount of pressure exerted to move 1 column of water by 1 centimeter. So the way that this, for example, we're going to look at it later in another format to see how that is done. The pressure is measured with water. You basically have an instrument like this. I don't know if it's clear or not. Yeah, it should be clear now. And then it has liquid, it has water, or sometimes mercury. And then you blow on one end. As you blow, you are going to push down on the water, and the water is going to go up on the other side is going to rise. The distance the force that you use to move 1 column of water from 1 point, by 1 centimeter, that is called pressure. Now, what is sound? How does it work? If you understand the definition of sound as we define it scientifically, you are going to kind of wonder why in the world they ask you this joke or this, they say, if you are in a forest, if you are not in a forest, no one is in at the forest, and a tree falls, will that tree make sound? So people who kind of come up with these things, they look at sound as it is something that you hear, that you can hear. But they misunderstand the point. Audible means can be heard, is possible to hear if you are there. So it doesn't mean that you have to be there for it to make sound. So the answer, yes, whether you are there or not, whether you are in the forest or not, that tree falling, it will make sound. It doesn't matter if you are there or not, because the word is audible. It's like this apple is edible with an E, edible. It means, you know, it can be eaten. It doesn't, you know, matter if you or a horse or anything eats it. It is possible to eat. It is food. So sound is an audible disturbance, is a disturbance that is possible to be heard if someone is there. And that disturbance can happen in a medium like gas, liquid, or solid. So this disturbance changes if we speak about air, because we obviously live in air bubble, and as we speak, we move air around, and air generates or makes sound for us. So the disturbance changes normal air pressure. Air pressure. We are going to speak about three ways. I mean, look at air pressure in three different ways. There's atmospheric pressure, which is, the symbol for it is P atmos, comes from French, pressure atmospherique. So atmospheric pressure is the normal pressure at sea level, at zero temperature, at freezing temperature. That's atmospheric pressure. Like, say you go stand, you don't have to be standing next to the ocean. It could be, you know, if you live on a, you know, this 5th floor. Basically, it is, you know, and near the ocean, for example, the level of the ocean, then that will be atmospheric pressure. However, as you go up, as you rise, say climbing a mountain, atmospheric pressure is going to decrease and decrease and decrease. Again, atmospheric pressure is the pressure measured at sea level at zero temperature, 0 centigrade, at freezing temperature, 32 Fahrenheit or 0 centigrade. If the pressure goes lower than atmospheric, then we call it negative air pressure. If the pressure goes higher than atmospheric, then we call it positive pressure or higher pressure. To understand this, think about pressure as crowding. Like you are in a classroom, 10 people are in a class. Obviously, there's a lot of space and they are not crowded. Then 20 or 10 more people come into the class. Will you have more pressure or less? Of course, you have more pressure because they will be crowded and the room has not changed its size. Let's say you have in the same room, you have 10 people that you started with. 5 of them leave. Will you have less pressure or more pressure? Of course, you are going to have less pressure, lower pressure. When you speak about air pressure, air is basically the molecules that we breathe in and out, and air has weight, and heavy molecules of air tend to go down closer to the ground because of gravity. The earth, gravity attracts them down. This is why molecules like oxygen is heavy. It sinks to, to the ground, and we are able to breathe it in and out. Hydrogen is not near the ground. Hydrogen is way like in the atmosphere. And helium, this is why when you go buy a birthday balloon and fill it with helium, if you let go of it, what's going to happen to it? It's just going to rise. I am going to say something. So now I asked you to, your homework that I asked you to do is I didn't write it down, is to listen to someone, and as you are listening, turn around gradually until your back is to that person, and tell me what happens to the sound. Will it increase? Will it decrease as the angle is changed? And I'd like you to explain why, it is the loudness of that sound is increasing or decreasing. Your second homework assignment is one second, froze. Is to answer this question about the helium balloon that I bought several years ago. It was in the winter, and someone had a birthday right in the middle of the winter, January. And I went into one of these stores and I, bought the balloon, and it was nice and filled and just really, kind of completely filled. And then I stepped outside with it, walked into my car, and it just shrank and almost lost it was like one size, and it was not full anymore. And I said, what in the world is going on? That was before studying speech and hearing science many years ago. So I rushed back to the store. I was angry. This balloon has a leak. What are you selling me? And I go into the store, and the thing just puffs up again, and it is full, and it is just, very tight. And I didn't know what to say. And then I walk out, and the thing just deflates again. Luckily, when I went to my car and I shut the door and put the car on, the balloon is back again. So what made the balloon shrink when I stepped out? I'd like you to try to answer that question, and we'll discuss it more in the class. So I have 2 questions so far that I'm expecting to have a discussion on in the first class. So again, the way that air pressure works, there are more air molecules near the surface, where we breathe and stuff. And as you go up, the higher you go up, the less air you are going to find. Because air has weight, you have less weight, you have less crowding as you go and rise up in the atmosphere. When you are on an airplane, especially traveling long distances, and it is, say, 50,000 feet, you are going to feel it as it goes, it's 50,000 feet, especially as you start to descend, or as you start to go up, your eardrums are going to be sucked out, because the pressure outside is very decreased. And when there's decreased pressure, it will cause suction. It will pull your eardrums out. So air pressure decreases as you go up into the, higher. And as you go lower than air pressure, like say, there's an area, like say, deeper into the earth, like going down to the Dead Sea in Jordan, for example. As you go down, that's the lowest point on earth. You will be sitting next to someone next to you. You will not be able to hear your voice, your own voice, not even speaking about the other person's voice. Because as you go down, there's so much more air weighing down on you and forcing itself into your ear canal and pushing on your eardrums, that the eardrum is pushed inward, forced inward, and it can't vibrate well to get the sound, to vibrate in response to the sound of someone speaking next to you. So usually, always negative pressure, negative air pressure makes suction, causes suction, and positive causes, pushing in. Air flows in a kind of a steady laminar way, like moves in a systematic way from one side to another. If you have a room that is closed, the windows are sealed, and there's no one going in or out, air is moving all the time, goes around, and then, goes up, goes down in a very systematic laminar way. Once you open the door, you push air molecules in, and that makes waves, air waves. If you speak, your muscles are going to generate a force, and that's going to push air molecules, and they will go up and down, up and down. So, sound is disturbance of normal air pressure, and that disturbance carries the signal from one person to another. Laminar flow, again, is steady and even, and it doesn't change. Like if you have a machine, it's going to say, ooh, no change in force, and the speed is the same. Usually, laminar flow helps us make vowel sounds. Ah, e, in a steady way, continuously, non-stopping. Turbulent flow. Turbulent flow is like having a river, and in that river there's a big boulder, and water is flowing from one direction. As it is moving, then it comes closer to that boulder and it hits. As it hits, what happens? It's going to bounce back, creating waves, and it will create what is, like eddies. It will go around the boulder, but in that process, you have waves all around the boulder. So that is called turbulent flow. As you obstruct the sound, different things, the sound hits a barrier, bounces back, goes up, goes around. So turbulent flow is used to create consonant sounds. A consonant by nature is a sound that is produced by an obstruction. So when you say, so obstruction, you close the airway completely and then explode, open your lips and explode them, and then you get a sound. So the obstruction can be complete or it can be partial, like this. I'm going to make an obstruction, but not a complete obstruction. Oh. So again, consonants, always you have some kind of obstruction that is going to create turbulence and the flow of the air. now we are going to, things are going to start to be more kind of interesting now that we are moving from the concepts to more kind of interesting stuff. Boyle's law was discovered by Sir Robert Boyle from Britain, and he discovered it. You can look here in the 1860 or so. No, he was born in 1860, 1627. It was discovered somewhere in the 17th century. So once you start 16 something, that is the beginning of the 17th century. Based on that, he discovered a law that enabled us to make trains. And based on that law, he was the one who actually he designed this steam engine that, later became the train that as we know it today. Boyle's law has two pieces, and it says, as the volume of an enclosed space increases, air pressure within that space goes down. That's one piece. Given certain conditions, given that the temperature remains the same. Okay, I'll go back to the balloon. Many students make a huge, big mistake. When they give me the definition, they do not say enclosed. And that basically makes their answer completely incorrect. So I'll show you the difference. This is a balloon. You notice the top is, the neck of the balloon is open. There's no obstruction. There is air inside of the balloon. And the pressure there is air, atmospheric pressure. There's no change. The pressure inside is equal to the pressure outside because the thing is open. So if I have air inside of it, and I force air in, if as the volume of a particular enclosed space increases, air pressure in that space decreases. So let's say now I trapped an amount of air inside of the balloon. If I manage to expand the balloon, say expand it from this end and expand it from this end and that end, I am going to have less pressure inside because I created more space and the same amount of air is there. So the air molecules will have more room inside. They will be less crowded. If I shrink this, kind of put my hands around the balloon and I compress, what is your expectation? What do you think? Yes, it is going to explode if I continue to do that, because I am narrowing the volume, making the volume, the space less, and that puts pressure on the air. It makes it more crowded inside. And if I continue to, put more pressure, that, is going to explode the balloon. So with this, now let's read the definition again, or the law again. As the volume of a particular enclosed container, space, increases. Like I said, if I expand the space, holding the same amount of air, expand the space, I'm going to have less pressure. And obviously, if I do the opposite, I will have the reverse conclusion. So, given that the temperature remains the same, Why are we saying that? If you heat the air, every molecule of air is always spinning around. Air doesn't stay still. It's spinning around, it's spinning back, forth, sideways, moving around. And every molecule has its own force, elastic force, and it has its own kind of space. So if another molecule comes closer to it, it's going to go away. If, so it keeps its own distance. It doesn't want other molecules to come close to it unless you force them. When you heat them up, they do not want to, they expand the field. They expand their boundaries. If they are, if the air is heated up. So they want more room and, to spin faster and go around faster, up and down, sideways, faster. This is why when in the summer, when this, it's very, very hot, you are going to have, not as much oxygen near the surface because the air tends to rise. In a nice, crispy, cold day, you have more oxygen near the surface. You are going to, have much more fun breathing oxygen, or in the morning. So let's see how this works. Again, the rule here is that what this law is saying is that volume and pressure are inversely related. They are related, but in an opposite way. So the greater the volume is, the lower the pressure is going to be. The smaller the volume is, the greater the pressure is going to be. So in this demonstration here, look on the left. You are going to see a container that has air molecules. And on the right, you have a container that has exactly the same air molecules in number. But what is the difference? So yes, obviously, the left container has more space. So he's 1, 2, 3, 4 centimeters cubic. And then on the right, you have 1, 2, 3, only 3 centimeters, even though you have exactly the same number of air molecules. The temperature, is it the same or different? 300 Fahrenheit, 300, the same. So there's no change in temperature. Now, what is the only thing that is different? So now look at the pressure value. This has 1 point pressure. This has 1.33. So which one has more pressure? Obviously the one on the right, because it has less volume and it has the same amount of air. So again, as the volume of an enclosed container space, again, if you do not say enclosed when you define Boyle's law, that entire law is not valid at all. It will be just, that definition gets a 0. Because that law, it is not anymore Boyle's law. And when we speak about a physical law, it is something that is, every single word in it is critical. It takes hundreds of years to come up with a law like this. And it summarizes so much. And again, if you leave one single word out, the entire thing is meaningless. So now see it in action. See that inverse relationship. The greater the volume is, the lower the pressure. The lower the volume is, the greater the pressure. So I'd like you to understand it really well and know how to define it, because it is really critical. It is a very important principle. in speech and hearing and everything that we do. Then the concept of compression and rarefaction. Compression is an area, it refers to an area of positive pressure resulting from collision of air molecules. Air molecules, we said they bounce around and float around. So when an air molecule just is being pushed, it is going all of a sudden to just invade the space of another molecule. Bang, and it will physically hit it. Now, if it is, once you hit it, this air molecule is gonna, go flying away. As it goes flying away, it is gonna hit another air molecule. Once it does so, it's going to bounce back. So whenever an air molecule moves from its location, it is going to go away, hit another molecule, and then go back again to where it was. When I speak, obviously there are millions and billions of air molecules, and we are not speaking about a single one. We're speaking about one as to make the idea simple. But when we speak, we move, millions of air molecules, push them away, and they come back to us. But let's take one. So we move the muscles, and they vibrate, and they hit, a wave of, a column of air molecules. That's going to move and hit another column, and then they are going to bounce back to me. That is repeated, like imagine dominoes that are lined up, and you hit, and then they start to bounce back. They hit each other, and they bounce back to where they were. That's just like that. So the molecules near me do not travel all the way down to your ear for you to hear my sound. No, they pass, each one is going to pass this, the sound to another, and will go back to where it started. Let's see. So now we're looking at, a demonstration. Here's where you start. You compress. When the air molecule is pushed and into and touches another air molecule, there's no gap. That is compression. As they bounce back, there are gaps in between. These gaps are bigger. Look at how big they are between one another. You have to really look carefully. As they are now, look at this at the space now, and look at how big it is when they bounce back. You are going to find that the space when they bounce back is twice as big as when they are now standing like that. And the reason is this. Let's say, I don't have two things to, let's say here's one air molecule, here's another air molecule. And they are 1 foot apart from each other. This air molecule is going to be compressed, will be hitting the next one. When it hits it, two things are going to happen exactly at the very same millisecond. They are going to hit it again. This one is, is not doing anything. This one is going to be pushed to hit. So when it hits, at the moment of impact, this molecule that hits is going to bounce back let's say 1 foot, because there's a distance of one foot here. And I take this molecule and shove it, push it away 1 foot so it can reach this one and hit it. Now this first one is going to go 1 foot back, to where it was. At the very same time, the one that is being hit is going to travel 1 foot away. So again, one molecule will go back 1 foot. The second molecule that is being hit is going to travel 1 foot away. Now, how many feet of a distance do I have between the two molecules? 2 feet. And that is rarefaction. We created a space that has less air molecules in between. And when they hit each other, there is no space. So that is compression. So I hope you understand this concept both concepts. So you can see now, there's always, when sound is transmitted, we always have one area of compression. See that compression, that little circle, that has the same has more molecules in it because they are all compressed, they are all smashed against each other. And the area that is like a spring in between, it has some, but it doesn't have as many, so it has less air pressure in there. So always they alternate. A single compression followed by a single rarefaction, followed by a single compression, followed by a single rarefaction. You will never find two compressions together or two rarefactions together. No. Each one comes, you have one compression followed by one rarefaction. One compression, one rarefaction. Always, always like that. So now, that thing moving in, that half moon here, it symbolizes your eardrum. So the air molecules, compression is red, means more air molecules compressed together. And then rarefaction are these bars in between, it means less air molecules. So then the sound wave comes in, it hits your eardrum, pushes it inward, and then the air molecules bounce back again with rarefaction, and then the eardrum bounces back. So that makes the eardrum go back and forth, and it repeats the same wave as that is coming in. Elasticity, inertia, and friction. Now, we studied elasticity, we studied inertia, we did not study friction, but friction is the resistance that is produced to slow down, basically to slow down the movement of things. When air molecules are disturbed, these three forces, elasticity, inertia, and friction, work together in order to keep the molecules going back and forth in a predictable way. When we say a predictable way, that means in a pattern. Pattern means happens and then happens again in the exact same way. So let's say there's, explain this. There's an experiment. There's a wall here, and there's a table. And on the table, you are going to put an object, say a piece of metal, and you tie it to a spring, and the spring is tied to the wall as you see. Then there's a kind of an arrow, and next to this, you could go, like some kind of ruler or some kind of measurement here. Now the arrow is next to the B, and you could see here's one A, B, C, 1 inch, 2 inches, 3 inches. When we take that mass, that little metal plate, and pull it backwards, let's pull it from B to C. What is your prediction? What's going to happen now when I let go of it? When I let go of it, it comes, I originally pull it back to reach where the arrow reaches is across from the C. So I move it back by 1 inch. And I let go. The thing is going to travel back from C to B, and it will not stop there. It is going to shoot beyond the A, and to reach from B to A. So now instead of moving it, I moved it only 1 inch, and I got it to move back to produce 2 inches of movement. It's gonna go from C to A, And then from C to B, and from B to A, all the way to A. And then it is going to bounce back again to B, and it will bounce back beyond B, but it will not reach C. It probably will reach, somewhere in here. And then it's gonna keep going back again past B and bounce back again, but it will never reach A. Again, it will be somewhere in between here. And then it keeps going back and forth, and keep back and forth until it finally is gonna stop at the B where it originally was. What made it behave like that? What made it, I'm going to explain it more in the next couple of slides. But the idea is this, simply. When I pulled it back, as I kept pulling it back, elasticity in the spring increased. As I pulled it back, I increased, the elastic force that wants to bring back, the spring to its original position increased. And when as soon as I let go, elasticity pulled it back again to its original position. But as it kept going back to the original position, the elastic force would decrease. And inertia, here's the resistance would decrease, and inertia is going to increase. What does inertia do? That thing is bouncing back again to the point where B is. And inertia says, yeah, you are moving, keep going. And inertia doesn't want it to stop at all. It wants it to run forever. And that thing is going to keep bouncing because of inertia. Here, there is no elasticity at B now. Elasticity is 0 and no resistance. But the thing is moving, so inertia is going to make it cross over, go to the other side, all the way down to A. And then as it bounces back to A, then at that point, as you go from B to A, the farther you go from B, the greater the elasticity will be again. The farther it goes from B. Until it reaches A, then elasticity is going to say, no, you're not going to go there anymore. You're not going to cross this point. And then elasticity will make it bounce back again to B. But when it comes to B, inertia is going to say, no, keep going. And then elasticity will resist, and it will overpower inertia and bring back the thing. So it is a mutual resistance between inertia and elasticity. One goes one direction, the other goes the other direction, and that causes the air wave to keep moving back and forth until basically they bring down, both of them die down, and then the thing goes down to 0, to where it stopped because of gravity initially, or friction. Hooke's law says Hooke's law says the degree of elastic force is proportional to the distance of displacement. So and the other piece is it acts in the opposite direction. So what does that mean? I have a balloon, and I'm going to displace the balloon. I'll pull it away with this end moving, this end is still. Go away. So the degree of elastic force is proportional to the distance of displacement. As I pull the balloon a little bit, there is resistance, but it's not great resistance. The farther I pull, the greater the resistance. So let's read again. The degree of elastic force is proportional to the distance of displacement. That means the farther I pull, the object away from rest, the greater the elastic force that will try to bring it back to its rest. I hope this is clear. What is the other part of Hooke's law? Is that the elastic force always acts in the opposite direction of the movement. So my movement, I am moving away, I'm moving the object away from rest. And elasticity is gonna move back to rest. Okay? So in the opposite of the movement, elasticity, the elastic force acts in the direction that is opposite of the movement, where the movement goes. I'm going this way. Elasticity wants to bring me back to the rest position. It is very critical that when you have a law like this, to know it, understand it first, make sense of it first, and then you can memorize it, because if you change a single word, the whole thing is useless. It doesn't produce the effect it is intended to produce. So again, the farther an object is displaced from the original position, the greater the elastic force that will pull it back to its original position. Let's I explain more, as I said here. Let's say there's a swing or a pendulum or whatever. Let's say a swing. And the swing is here. You take it and displace it. You pull it away from rest, say by 1 foot. It could be 1 inch. Let's say 1 foot. At rest, when the thing is hanging down like this, there is no resistance of any kind. The thing is hanging down. Nothing is bothering it. There is no resistance. But the minute I start to displace it from its original position, the more the resistance that I will have. The farther away, if I move it by 1 inch, it is going to have elasticity. But if I move it by 1 1/4 of an inch, we'll have greater elasticity. 1.5 inches, greater. 1 3/4, 2 inches. The greater the distance, the greater the elastic force is going to be. You can calculate it, you can predict it. So here's 1 foot. As I move away from rest, rest has zero elasticity. There's no elastic force there, no resistance, nothing at all. And as I pull the thing away, displace it, I have greater and greater and greater and greater elasticity. So we stop here. As we let go, now the object is going to start moving to rest. What happens to elasticity? Will it increase or decrease? As you go back to rest, elasticity will decrease, decrease, decrease. When you reach rest, it is at 0. There is no resistance. So the thing says, well, inertia is going to be saying, well, if there's no resistance here and you're moving, keep moving. Because something that is moving wants to move indefinitely, until something else stops it. So the thing is going to swing past rest, keeps going, 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 going. As you start moving away from rest, elasticity will gradually increase and increase and increase and increase and increase. What happens to inertia as you go away from rest? You should say it decreases. So inertia, as you go from rest, inertia decreases. Elasticity increases. And they are acting in opposite directions. Elasticity would like the thing to stop moving. Inertia would like the thing to continue moving. And that resistance is what makes the wave constantly going, or like a pendulum. Then you reach the point, an equal point on the other side. So 1 foot, we had 1 foot here, then you go to rest and overshoot 1 foot on the other side. At that point, elasticity will say, no, you're not going to go anywhere. I'm strong enough now to prevent you. And inertia is going to reach zero. The thing is gonna bounce again because elasticity is strong. It's gonna pull it back to where it was. As you keep going to rest, what happens to inertia? It is going to increase and increase and increase and increase and increase and increase because elasticity is decreasing, decreasing, decreasing. When you reach the point of rest, now which one is weaker? Which one is the one to be overcome? Elasticity is going to be overcome. There's no elasticity now. And inertia is going to say, now I can overcome elasticity. And it's going to make the thing keep going beyond rest. And it will just by this time, it will have lost some energy because of friction from gravity and friction of air. It's not going to be able to travel the one whole foot that we started with. It will lose a certain amount of energy. And then it keeps going back and forth, back and forth. Eventually, the thing is going to stop on its own. So you have this pattern. The first wave is the greatest one, from 1 foot to the right, 1 foot to the left. The second one is less. And the third one is less and less and less and less until you reach a point of no movement again, like the starting point. So you could see that gradually, systematically, due to friction or what is known as damping, the wave will decrease and decrease until, it becomes smaller and smaller in a systematic way until it completely stops. And you could take this and reverse it. Basically, that if you reverse it and bring this here and this here, that will be basically like this. So a sound wave is just like a pendulum, but it is shaped like a Z, an inverted Z. Here, I'll explain to you how. This line, excuse me, the horizontal line is the rest area. Like here, that vertical line is rest. Horizontal on the sound wave spectrograph is rest. And let's say this is a guitar string. When you pull the guitar string and make it reach B, as you pull it away from rest, keep pulling and pulling and pulling, and it reaches this point. Elasticity is going to increase and increase and increase and increase until you cannot go anymore. Again, as you go from this point, the rest, to the other side, inertia is going to decrease and decrease and decrease and decrease and decrease. Now, after that, you let go, and the thing is going to bounce back again to rest. Bouncing back to rest. As you go from, towards rest, what happens to elasticity? What happens to inertia? All of these are exam questions. You need to understand this really, really well, because this is how a wave is kind of generated and how it behaves as a result of the three things: elasticity, inertia, and friction. As it reaches rest, the guitar string is gonna keep bouncing, on to the other side, because inertia becomes very strong, elasticity reaches zero, and then the thing overshoots to the opposite side. And it keeps going and going and going and going until it reaches the same exact point. Like, say, if that was 1 inch away, on the opposite side, it will go by 1 inch away. So, but as you go from rest, again away in the opposite side, you are gonna have elasticity will increase, and elasticity will increase, and inertia is going to decrease, like we said before. And then it keeps going up and down, up and down. So the peak here, that peak is called, it represents the maximum displacement. the maximum distance that the thing was displaced by. That peak also is compression, because you are compressing, you are making more pressure here. And now the peak below the rest area, this is called trough, T-R-O-U-G-H, trough. The trough here, like horses used to feed in a trough. If you go down to downtown Bridgewater, in the center of the town, where the Route 28, Route 104, and 18 intersect, the old trough where horses, they put water and feed for horses, it is still there from 1840. It's an ancient, thing. And so a trough is like a, similar to like a sink, down. So that area here stands for rarefaction. Rarefaction below the line, it stands for rarefaction, because you kind of got this as something extra. You didn't put new energy to make it. You took that object, that guitar string, pulled it up by 1 inch, all that you got. Logically, you should just let go of it. It should go back to rest, and you get the 1 inch that you put in. But no, because of inertia, it's gonna make you add another inch on the other side. So again, the peak stands for compression, the trough stands for rarefaction. And one compression, one trough, they make a sound wave. So from A to B, here, B to C, that is the trough. Yeah. That it shows you how loud a sound is. And then as you go down to the opposite side, you have the trough. When you come to the point of E here, the end of the Z, that is a complete sound wave, an inverted Z. And then you can see that there's another sound wave. Here it starts, the second sound wave, and then the third one, it starts here. It is not showing. So you have 2.5 sound waves. So the peak tells you the loudness of the sound, otherwise known as the amplitude or the maximum point of displacement. So maximum point of displacement is the same as amplitude. It tells you how far the thing is displaced, and the greater the distance is of displacement, the louder the sound is, the greater the amplitude. Damping is the gradual decrease in amplitude or in the maximum point of displacement because of friction, as I showed you with the swing coming down gradually to a halt. So sound waves are propagated in a global fashion, like this. So you could see the center here is where you make the sound. You are standing there, your vocal folds are active, and you say something, and that is going to displace, the first bubble of molecules that is near your body. That bubble is going to just go out, up and down, back and forth, all directions. It will compress against another outer bubble, and that is going to compress against another outer bubble, and bubble after bubble after bubble. So eventually, every bubble that you displaced is going to be coming back again, and after displacing another one around it. The point at the very outer limits of that sound wave, we call it the wave front. The point at beyond or at which the sound cannot be heard anymore. And of course, obviously, the farther you go away from the sound source, the softer the sound is because of the energy being lost due to friction of air and gravity. So the sound again travels up and down, sideways, back and back and front in all directions, like a globe in all directions. Here are some websites you can browse to, they have some interesting information if you would like to learn more. And please do read the chapter in the book and understand it. It is really important. So you are responsible for the book, textbook, the chapter that's assigned, as well as the lectures, and also any notes that you take in the class. So this ends this section. I spent a long time because I wanted you to, wanted the explanations to be clear. I understand that you need to refer to these more frequently. We'll remember your homework now are two things: listening to a person and identifying, seeing if the sound decreases or increases as you turn away, and also answer the question, why did my birthday balloon, why did it become smaller when I went out? It was not floating at all. It was not gonna escape. And again, it was in January. So I will discuss this in class. Thank you.